Hi, welcome to Turkish Engineering. In this lecture, we are going to study projectile motion. As I said before, projectile motion is just a simple application of acceleration in a plane. It will be just a special case, for acceleration in a plane, which was our topic in 3.2. 3.2 was acceleration in a plane. This one, okay? So if you didn't study acceleration in a plane, which was our topic in 3.2, please go back to previous video to study acceleration in a plane. When you understand acceleration in a plane, you can understand easily how projectile motion happens and how can you apply the rules which you took before. So I will put my axis, y and x axis, okay, because it will be just motion in a plane, okay. I must have two axes, so two directions, which is y and x directions. It's projectile motion and 2D. Actually, projectile motion cannot be in one dimension. Projectile motion can only be in 2 or 3 dimensions. So I will skip 3 dimensions, okay. We will not study in this course dimensional projectile motion, but we will study 2-dimensional projectile motion, okay. So it will be inshallah easy. So I will put our special cases, okay. The first special case for projectile motion, actually you are throwing an object, okay. Just assume that we will start from let me just make this. So we will start from origin, okay. So I will throw this object with an initial speed, okay. That will be like this. So it will go up, but slowing down in the y-axis. Why? Because I will have an acceleration, which is gravitational acceleration in the y-axis, okay. So I'm putting my path. My path will be like this, okay. So I will put some rules here, okay. Some special cases which are for projectile motion only. So my acceleration in x must be equal to 0. Why? Actually, when you throw an object in the earth, so if you are throwing it in vacuum, there is no air, so there will be no any resistance in the x-axis. If you are throwing any object in vacuum, that means this object will not have any force component in x. There is no force acting in the x-axis. So that means there will not be any acceleration in the x-axis. Actually, it's not happening in the real case. We are not in vacuum, so we have air, right? When you throw something, you will have an air, so you will have an air resistance, which is drag force. But in our applications, to simplify projectile motion examples, we will assume that the air resistance is neglected, okay. So air resistance will be just 0. There is no air resistance and there is no drag force. So I will neglect this drag force. And just note that in some cases, air drag will be too small, so it will not affect our projectile motion. Actually, this will be nearly equal to 0. So in a lot of examples, in a lot of applications, you can neglect the acceleration in x, so you can solve some real problems, and when you calculate, so you will get very near to exact solutions. But when you study more physics and just improve your skills, so you will take projectile motion when acceleration x will not be equal to 0, okay. So you will study drag force and how it affects our projectile. But in this case, for simplifying projectile motion, we will neglect air resistance. If there is no force acting on this object in the x-axis, nor positive or negative, so acceleration in x must be equal to 0. So not the first rule, okay. This is the first rule. Acceleration in x must be equal to 0. What about the second rule? Actually, the initial velocity in x must be bigger than 0. Why? If you are throwing something and you don't have any initial velocity in 0, you don't have any initial velocity in the x-axis, that means you must throw it up or throw it down. So you will have only initial velocity in the y-axis because your initial velocity in the x-axis is 0. In this case, that will named as free fall, and it is not projectile motion. So I must have a motion in the x-axis. So for having a velocity in x-axis or displacement in the x-axis, I will need acceleration in x if I'm at rest. So in this case, there is no acceleration in x, so I must have an initial velocity. It is very important. If there is no initial velocity in x, so it will not move in the x-axis since there is no acceleration in the x. So in our cases, you will see that there will be a certain amount of initial velocity in x that will make the object moving in the x-axis. So the third rule, which is related by the first and the second rules, our velocity in x will be always equal to initial velocity of x. You can put here final, or you can put only vx. So when time equals to 0, when time equals to 1 seconds, when time equals to 2 seconds, when time equals to 3, 4, 5 seconds, so always my velocity in the x will be constant and will be equal to initial velocity in x. Why? It is coming from our rule from the previous videos. As we said, for the kinematics equations, we have v final will be equal to v initial plus acceleration times time. So as you see here, since there is no acceleration in the x-axis, I will get this one will be equal to 0, this one will be equal to 0, so v final will be equal to initial velocity. Okay, v final will be just equal to initial velocity. It is coming from there. What about the fourth law? Okay, let's put our fourth law. This is simple, just a simple idea, you will understand it. If our initial height, okay, just put delta y, okay, just put delta y, or I will put y initial. Our initial position in the y-axis, here in this case it is 0, right? But it can be 5. So when you throw this object from the initial height, which equals to 5 meters, for example, from here, so you will have an initial height. If your initial height, okay, equals to 0, okay, if equals to 0, so acceleration, the velocity, initial velocity in y must be bigger than 0. What's it actually? I will inshallah explain so you will understand. If my initial velocity, if my initial position is 0 in this case, and there is no velocity in y, okay, there is no velocity in y, actually I will slide in the x-axis. Okay, if I'm just on the ground, and I'm moving, so that means I will slide on the x-axis, and there is no velocity in y. It will be 0, and because of the you are on the surface of the earth, so the gravity will not make you move. Okay, so you will not move down because you are on the surface of the earth. There is no space to move down. So if your initial velocity is 0, you must have an initial velocity in the y, which is positive. Okay, but if the case was not like this one, so your initial velocity is not 0, so you will start from initial height like this one. Okay, maybe you will have just only x component of velocity. There is no y velocity, but it will be treated as projectile motion. Why? Because in this case, actually, in this case, when you have only initial height and you have only x velocity, this case will be half of our simple projectile motion. So when you are in this point, actually you have a velocity in the x-axis and there is no velocity in the y-axis. Okay, so this one is similar to this one. When you are starting your motion from initial height and there is no velocity in y, so this object will go down like this, right? So it will be just similar projectile motion examples. Okay, just put like this. Oh, I'm very bad for drawing these lines. So it will be just hit the ground and complete its path like this. So just 4 simple rules. Actually, I'm giving these ideas. You will not you don't have to write these rules like equations, okay? But these are our special cases for projectile motion. Okay, so note that there is no acceleration in x. This is always in our examples for projectile motion. This always happen in our projectile motion problems. And initial velocity in x must be bigger than 0. So you will see in our problems, and the x will be always equal to velocity in x always equal to initial velocity in x. So there is no because there is no acceleration. And the fourth rule, I must have an initial height if our velocity in y equals to 0. Okay, if the velocity in y, there is no velocity in y, I must have an initial height. But if I'm beginning from when initial height equals to 0, there is no initial height, so I must have an initial velocity in y to push me up to so for making this motion as a projectile motion. But if there is no velocity in y, as I said, this object will slide in the x-axis, so it will be just one-dimensional motion, and there is no projectile motion. So just understand the spatial cases. And what about just a simple fifth rule, which will give us acceleration in y? Acceleration in y will be equal to g. Okay, so our acceleration will be always constant, negative 9.8 meter per second squared. This is the gravitational acceleration in the Earth. If you are studying a projectile motion in the moon, actually this is not the case. We will not study projectile motion in the moon because it's not applicable for us. The applicable one for us to study projectile motion in the Earth, so, because we are throwing some things in the Earth, right? So we will use this one. Acceleration in y will be equal to g, and it's negative 9.8. Is it always constant? Actually, when you go to high altitudes, this gravitational acceleration will slow down. So okay, will decrease until the maximum height of the atmosphere. So you will get 0 acceleration in y. That means when you go outside of the atmosphere, so any object will move without any force pulling down. So you will go easily. If you have initial velocity when you go outside of the atmosphere, so you will keep going without any resistance, without any stopping effect. Okay, but in our cases we will not study high altitudes. We will study just 20 meters, 100 meters, maybe 200 meters projectile motion. So in our applications, the gravitational acceleration will be constant. Okay, note that in this level, introduction to college physics, you will not study variable acceleration in y. So acceleration in y must be equal to a constant value, which is minus 9.8. Okay, and it will be given in our questions, or you'll just memorize it. When you make a lot of examples, solve a lot of examples, you will memorize this value simply. Okay. So we understood now about the spatial case for projectile motion. So now it's time to put our equations, kinematic equations for projectile motion. So I will take the case here, just a projectile motion, to see what's our formulas. Okay. Now I'm going back to acceleration in a plane, which is 3.2. I will take some formulas from here and apply our spatial cases for the projectile motion. Okay. So let's take some formulas from here. Actually, these all will be used. So I will take these and go back to them. Okay. So I will put our formulas which are coming from acceleration in a plane. So here, let's take these to other side, and this one to here, and this will be just positive. Okay. So actually, since there is no acceleration in x, okay, it's just like this. V of x equals to Vix plus at. Okay, just take this again. Okay, I will put Vf equals to Vi plus a times t. Just apply this rule for the x-axis. Vfx will be equal to Vix plus acceleration in x times time. Actually, in this case, in our spatial case, acceleration in x will be equal to 0. So this 0 times time will give me 0. So this is the case. Final velocity in x will be always equal to initial velocity in x. What about the final velocity in y? Final velocity in y will be equal to initial velocity in y plus acceleration in y times time. As you know, your g value is minus 9.8, so you can put your value here. Acceleration in y, just substitute minus 9.8. Okay, so I will put here minus 9.8. So I got two new formulas for projectile motion. Okay, these are our formulas for projectile motion to calculate final velocities. Okay, so this is for the resultant one. I will not use here. Okay, just these two. For calculating any final velocity in just resultant case, as you know, we have x-axis, y-axis components, and we have the resultant one, which is the summation of x and y. So when you calculate initial final velocity in x and y, you can calculate the resultant one. So the resultant one will be calculated by this formula, vfx squared plus vfy squared. As you know, this is coming from hypotenuse and Pythagorean theorem. Okay, so these ones actually I put, so I will just erase it. Okay, here I have just three formulas for now, and I will take this one. Actually, delta r cannot be calculated by this one here in our actually we can use it, but we will just choose to use x and y. Okay, we will analyze x and y, then we can easily calculate delta r. Delta r will be just displacement, so it is easily equals to delta x squared plus delta y squared. Okay, and in a square root. I will calculate delta x first and delta y first. So if I want to calculate this one, I will use this one. Actually, in our problems, I will not ask about delta r. I will not ask about delta r. Actually, the questions for projectile motion, in general cases, there is no application for delta r. We are interested in delta x and delta y. So I'm putting this one, but we will not use it. Okay. Here, these will be our just valuable formulas. Here, since there is no acceleration in x, half of 0 times time squared will be just 0, right? In x there is no acceleration, so I will erase this one, but I have initial velocity in x and time. Okay, so for any time to calculate delta x, our spatial equation, our spatial formula for projectile motion will be like this: delta x equals to v initial x times time. What about this case? I have initial y velocity, so it is not 0. I have time, right? And here, instead of putting ay, just put our value. As you know, our value, since ay equals to minus 9.8, so you will get another formula here. Delta y will be equal to v initial y times time. There is plus, but here I have minus. So plus multiplied by plus, actually this is minus. Positive multiplied by negative multiplied by positive will give me negative. So I will put here negative. Half of this value will give me negative 4.9 times squared. So this is our delta y formula. Okay, v initial y times t plus minus 4.9 times squared. This is one of our formulas which we will use. Okay, so I will put this one. Just slide down here. The final velocities for the resultant one, this one I will not use, but for x and y I will use. In this case, actually the final velocity in x will be equal to just initial velocity in x. So if you know initial velocity, this one, these are equal to each other, right? So when you don't have the time and you want to calculate delta x, actually your acceleration in x equal to 0. Your acceleration in x is equal to 0, so this will cancel. So you will get just vfx squared equals to v initial x squared, and actually this vfx equals to vix I put before. So this is not usable. This is not usable because acceleration in x equals to 0, so this formula is not applicable for us. in the x-axis. What about y-axis? Actually, this will be a powerful formula for us because we have an acceleration in y. So I will put the equation again, v final of y squared plus v initial y squared plus 2 times acceleration in y. Actually, that will be just minus, because ay is equal to minus 9.8. So just take 2 times of minus 9.8, it will be like this, delta y. This is one of our formulas which will be used for projectile motion in the y-axis. From this formula, let's get a new formula. Okay, actually, when this will be our last or near to last formula. Okay, the formula which is before the last. Okay, so I'm throwing something with initial velocity in x and in y with an angle. Okay, I will have an angle here, theta. So it will go up and slowing down in the y until it reaches the maximum height, then go down. So as you see, in this point, actually, our velocities in y for this case is just like this. Okay, this is v and this is vy and this is vx. Vx and in any point vx will be equal to just the same value. Okay, vx is not slowing down because there is no acceleration, but vy is slowing down. Vy is slowing down. In this point, I will have just smaller vy, and vx is similar. Until I get here, there is no vy. Vy is equal to 0, but I'm just like a sliding in the x-axis, only one component of velocities. When I reach here, my vx is same, okay, still same, but my velocity in y, because I'm falling in the y-axis because of negative acceleration, our velocity in y will be downward. And here will be downward but bigger. And what about x? Always same. It's not changing. When I'm reaching here, it will be vy, and here vx, the same one. So when I'm reaching here, actually, I will have the same velocity component, okay, which will has just theta, angle theta, but will be negative theta. Why? Because our vy down will be just equal to this one, okay, and vx always constant. So because of this case, you will see that when you reach to the same ground level, the same initial height, so you will see that your velocity angle, which is theta, will be same as the initial angle. But in these cases, as you see, our theta is always changing. Our angle is always changing. So it will not be equal to theta. And I have a different angle here, which is smaller than this one. When I reach here, our angle is 0 because I'm in horizontal way. It's just 0 degrees. Here I will have negative degrees, negative, negative, and slowing down in degrees until I reach here. It will be equal to angle theta. So just put an example, new rule for h max. Actually, when you reach here, this height h max will be equal to delta y max, because this is your maximum displacement in y. What about the range? I will put the range here. So starting from this level until you reach your ground level, okay, the same, you are hitting the ground. So this, okay, you will have a just length here, which is from the initial point for the final point. So this is delta x, and actually maximum delta x, because you will not go when you hit the ground, your projectile motion is done, it is over. Okay, so our delta x max must be equal to our range, which will be represented by r. So this is our range. Okay, this is our range, and this one is maximum height. So let's put some formulas about time max. What is time max? Time max means when this projectile motion reaches to that point. So what is the time when you reach there? Actually, time max will be equal to will be calculated by this formula. V final y is equal to V initial y plus, or what we put, negative 9.8 t, right? This is our formula. What about this point? Actually, there is no V final y, so 0 will be equal to initial velocity in y minus 9.8 time. So let's calculate for time max. Just send these values to the other side, so you will get positive 9.8 time will be equal to V initial y. So you will get your new formula, okay? T, which is here T max, okay, because you are reaching your when final velocity equals to 0 in y, that means you are reaching the maximum height. So T max for maximum height, your time will be equal to V initial in y divided by 9.8. This is a new formula, okay? What about the H max? How can I calculate H max? I will use this formula. I will just take this formula to find any way for H max. So here our V final y actually is equal to 0 in this case, right? When I'm reaching the maximum height. So let's put here 0. And this negative, just send it to other side. So you will get 19.6 delta y will be equal to V initial y squared. So delta y for maximum height, delta y max, will be equal to V initial y squared divided by 19.6. Okay, your delta y max will be equal to V initial y squared divided by 19.6. Actually, you can use a different formula. I will put this one. You can use different formula for delta y max. You know that delta y is equal to V initial times plus V initial times time plus acceleration in y times squared divided by 2. Half of acceleration in y times time squared. But here I know ay, so I can put our exact values. So I will put this one minus 4.9 times squared. So you will put here instead of plus, because your acceleration in negative direction, so you will put minus 4.9 times squared. So this is a different formula for delta y. Actually, when you put delta y max, you must put your time, you must substitute your time by time max. So delta y max for your maximum height, you will use the same values, okay? This is V initial y times time max minus 4.9 time max squared. So we have two formulas. You can select one of them and use. For delta y max, you can use one of these, okay? We will have two formulas. What about the range? What about the range? How can I calculate the range? I must know what is my total time. For total time, actually will be equal to our time max time 2. Why? As you see here, you are starting from initial point and coming to the highest point, okay? Then going down to reach that. The path which you take here, the length of your path is equal to length of your path is here. Actually, when you take a video starting from here to reach there and from here to reach there, actually you have similar velocities, same velocities, but in the just opposite directions. So this video, just make it reverse. So just put your time is going back, okay, the reversed video. So when you move video reversed, that will go back to reach here. Actually, this will be just flipping of your motion. So you started from here to reaching there. If you make the other your half of the second half of your projectile motion and make your video reversed, so you will start from here and reach there. Your path is same, your velocities are same. So you can say that the time for here when you reach there, your time will be time max, and here your time will be time total, right? So you can say that this time when you reach here must be equal to this time. So 2 times time max will give you total time, flight time, okay? Total time will be equal to 2 times T max. This is our last formula for time. And when you apply this rule for delta x, for calculating the range, okay, range will be equal to delta x max, that will be equal to v initial x times time total. Because there is no acceleration, it will be enough to just take the initial velocity and multiply it by your time, which is total time. You will find your maximum range, which is delta x max. So this is just an explanation for projectile motion, which is just one of the applications of the acceleration in plane, just a spatial case, as I stated here, 5 rules of spatial case. Then I put the formulas, okay? So just revise our formulas and put in just I put some proofs here. So I will take the usable ones without the proofs. So you will see how many formulas we have. We were here, so I will put a line to just see how many formulas we have. Yes, we are over now. We have just these formulas, okay, we will use them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have just 11 formulas, okay. You will revise them, and I will attach our formulas for projectile motion, so you can use them. Actually, we have just some 3 or 4 additional formulas which are coming from velocity in a plane. As you remember, we studied velocity in a plane, and you know there are some relations between velocity and velocity components, which is velocity in x, velocity in y. So we will use these simple ideas. For example, Vx will be equal to V cosine theta. Actually, we studied these ideas, so it will not be hard for you to memorize these additional formulas. I will putting them here, but these are not new formulas, okay? It's coming from projectile velocity in a plane. So we are over now. Just 3 formulas which are coming from velocity in a plane. Just chapter 3.1. So when you add these formulas, so you will be over just 11 plus 3 formulas. We have 14 formulas, and 3 of them you must know them from the previous videos. So we will use these formulas and solve projectile motion problems. So let's see how can we apply these rules onto projectile motion problems. See you in the next video.